We'll now look at a number of AI planners and the type of application in which they've been used. Earlier in the course we showed a table with a number of practical planners applied in realistic situations. We noted the long history of the practical application of AI planning methods. And during the course we've described some of the key techniques employed in such planners. We're going to now explore a number of these systems, the features they include and their applications. SIPE2, the System for Interactive Planning and Execution, was created in the 1980s and has been developed since then to provide a comprehensive approach to AI planning. It's been developed by David Wilkins and his colleagues at SRI International in California. SIPE2 is a domain-independent planner which supports interactive planning, allowing humans and system to cooperate in a mixed initiative planning fashion. It can efficiently reason about actions to generate a novel sequence of actions that respond precisely to the situation at hand. It supports the giving advice to the planner. It plans hierarchically at different levels of abstraction, replans during execution, can generate parallel plans so it can allow for multiple agent planning, posts constraints and reasons about resources within the plan, and interacts with users through a graphical interface. SIPE2 has been applied in applications as diverse as oil spill response, military planning, and production line planning in a brewery. OPlan was built by my own team at the University of Edinburgh through the 1980s and the 1990s. It was based on the features in the earlier non-LIN hierarchical task network planner. OPlan supported the whole life cycle of planning, from domain modeling and knowledge elicitation tools, through planning, detailed constraint management, and plan execution. It was able to repair plans or replan as necessary when execution failures occurred. And OPlan experimented with a wide range of graphical user interfaces, including support for multiple concurrent users with different roles in the planning process, and the workflows involved in coordinating between multiple users. It supported a web interface to allow the planner to be used as a web service. OPlan has been used at Edinburgh and elsewhere for a wide range of applications, some of which were introduced earlier in the course. And as noted previously, OPlan was used as the basis for the design of the deployed Optimum AIV planner at the European Space Agency for Ariane rocket launcher payload bay assembly integration and test. SHOP and its successor SHOP2 were created at the University of Maryland by Dana Now and his colleagues. SHOP2 is a hierarchical task network planner, but keeps the activities in the plan fully ordered. It selects activities to include in the order that will be executed from the start of the plan, which eases reasoning about the state of the world affected by the plan at any point. SHOP2 does allow for interleaving of the solutions for multiple goals and sub-goals in this ordered plan, which was an improvement over the original SHOP planner. SHOP2 can reason with a rich logical model of the state, including quantifiers and conditionals. It can maintain and reason about temporal constraints as is required for most practical planners, and it allows for numeric computations alongside the more symbolic world state models. Calls to external routines are possible to incorporate constraints expressed in program code. And the rich domain model allows for preferences on choosing operators in given situations, a feature seen in other practical planners also. SHOP and SHOP2 have been applied to a wide range of applications as diverse as fighting forest fires, controlling multiple unmanned autonomous vehicles, UAVs, and creating business process workflows. The SHOP techniques have also been incorporated in some domain-specific planning applications and embedded in manufacturing automated systems and in versions of the commercially available Bridge Baron device, which won the inaugural World Computer Bridge Championships in 1997. There are some common themes we can see appearing in many of the practical planners we've described. The use of an outer hierarchical task network approach which is friendly and understandable to users. An underlying detailed constraint handling layer to handle the real needs of time and resource constraints in plans. Integration with simulation and analysis systems to prune or further constrain the plans which are valid and useful. integration with plan execution and plan monitoring to put plans into real use, rich knowledge modelling languages and ways to describe features of application domains in ways which the planner can use to constrain choices, and the availability of comprehensive and useful user interfaces during planning and execution.